Hey everyone, how are you? Do we have sound? We have sound? Good. Just adjusting my levels. Okay, great. Actually, because people are still trickling in, I do want to make a comment about how there's going to be an exam in a week. I think it's in a week. And so I just wanted to talk a little bit about how that will go. I'm going to be honest. This is the first exam that I've ever given over remote proctoring, just because of the way that I've been teaching the classes since the pandemic began. This is the first exam I have to deal with. So I went around and tried to learn from best practices. And I wanted to just talk about this with everyone and give people a chance to give feedback or ask any questions as well. So first of all, I've actually shared all of the old exam problems that I've used. And so you can see from looking at them that they're designed in a way where they're generally quite hard to Google anyway. And they're designed so that actually, even if you have all of your notes, that's not really the most important thing. The most important thing is to learn how to think. Question? No? Yeah, so the exam is designed in a way which I'm hoping will actually make it pretty easy for people to be good people. I mean, of course, there's always the question of cheating. The exam happens to be one that's relatively difficult to cheat on. That's how it was designed. And actually, if you look at the exam, I also shared the previous grades. And you can see from the previous score histograms that, for example, solving 3 questions out of 5, that was pretty good. Solving 4, that's really good. And solving all 5, that's like nearly impossible anyway. So the way it's designed is that it's actually quite hard to cheat. I'm just saying this in a way because I want people to know that hopefully people won't be cheating in this class, and if they do, it probably won't help them much anyway, because in order to make your way through all the questions, given that no one can actually finish all 5 of them, there's nobody incentivized, I think, to go and cheat. But that said, the way that I want to proctor this is I went and asked to find out how these are usually done. And what we'll do is we'll do it over Zoom. I will request that you do turn on your camera. And then the camera, all that we ask is that, make it so that you're not like right in front of the computer and working on the computer. I'm not going to require that you print out the exam in advance. I'm not going to do that. It's just like, I'll put the exam up. Everyone can go to look at the exam at the right time. It will be a PDF file. You can scroll on it back and forth if you want. Please just don't sit on the computer and attempt to, I guess, do a whole lot of chatting and looking up stuff. In particular, please don't do any of that. This is supposed to be an exam. And I figure that should be enough, to be honest. And also, I just know from previous experience of administering this exam, if you spend a lot of time chatting with other people during the exam, you actually solve less problems. So yeah, hopefully it should be okay. Okay, so again, I want to add one more thing, which is that because of time zone issues, I know that some people are actually not even here right now because they have time zone issues, and so they're going to be watching a recording of this later. And so there will actually be 2 exam times. In fact, they are 2 completely different exams with entirely different problems. But let's just say you're recommended to take the main one. That's like the one right now. If for some reason you can't take that main one, there's a backup one, which is at 9 p.m., which is not an ideal time to be taking an exam like this. So strongly recommended take it at the regular time. If for some reason you do want to take it at the other time, please do let me know in advance, just so that I know who to expect. But this is the main one. Okay. Any questions? Yeah.
I just wanted to tell you that chat is disabled.
What? Chat is disabled? How did that happen? Oh no, how did I do that? Okay, thanks. I don't know how that happened. Hi, okay, good. I'm glad that you were able to just jump in. Hi, okay. Yes, you're free. Wonderful, wonderful. Okay, there was another thing I was going to say about the exam, which was, oh yeah. So the way it will work is the questions will all become available at 2:10 p.m. and at 2, what is it, if I could do math, at 3. At 3, then that's when you should be starting to take pictures of your problems or scan them in and then submit them. And all I'll ask is just keep the Zoom camera on during that time, so it's clear that you decided to stop writing and then you decided to take pictures and send it to us. And after you send it up on Gradescope, then feel free to sign off on the Zoom. And I think that should be enough to keep everyone honest. Question time. Ooh, Brian. Can we write our exams on a tablet? Oh, I would prefer you don't, only because of the fact that maybe just for fairness, I don't want that somehow on the tablet one can also be chatting with other people. So I'd prefer if you actually used paper and then took a picture of it afterwards. The only reason I'm doing this, honestly, is because I think that most people in this class want to do it for real, and it's just no fun if somehow you're doing it for real and then someone else like does something fishy. So please don't do that. About the open notesness, you've probably seen that I have open notes on all of these exams, but please, again, for the same reason, unfortunately, we have to print things out just so that we don't have electronic devices being used. Okay, question. Again, my vision is not very good, but is that Shania? Yeah, print out. Yes, 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 please. And I know this is terrible for the environment, but this was the only way to make it so that I guess everyone who wants to take the class for real doesn't have to worry about these things. Yes. So the format, it will be the same, 5 questions, 50 minutes. The questions will be of similar, like, out-of-the-box type of the previous exams. But honestly, if you go and practice by doing the previous exams, you'll be really, really good at combinatorics. And then whatever comes, you'll probably be like, oh, that was a surprising different angle that one could take on all of these things. And of course, like, don't Google stuff on the exam. I'll be trying to write an exam that you can't Google, but just like, don't do that, right? Let's just like do this like an exam. Are there any other questions about this or feedback? No. Okay, then we'll go on and continue doing math. But again, this will be the exam. There are 3 exams in the class. Then there's a 4th one, which is a final exam. And between all of these, then the grade will be done. So good. So let's go and continue talking about some math. Math time. Great. So I want to continue talking about all these different ways of counting things. And the last time what we did is we proved this inclusion-exclusion formula. So I'm going to open with an interesting question, which is it's a classic question. So if you've seen this before, please don't give everything away. But it's a classic question, and it actually is it's something called derangements. Derangement sounds like an arrangement, just like deranged, okay? And so the question is, how many derangements oh, how many derangements are there for n things? Well, for n things. Whoa, my pen is not behaving well today. Just a second. Oh, it's because it's not tight. Okay. For n things. What does a derangement mean? So, you know, like the number of permutations of n things, the number of arrangements of n things is n factorial. The number of arrangements is equal to n factorial. Whoa. Now, a derangement is something where I sort of want to do a permutation, I want to do a rearrangement, but I want to make sure that everything went into a different place. So a derangement, what this is that it's a permutation where everything went into a different place in the order. So maybe let's give an example, right? So what's an example of this? An example, if n equals 2, can anyone tell me the only derangement of 2 things? If we call the 2 things 1 and 2, what's the only derangement? Yes, 2, 1, I see it. The n equals 2, 2, comma 1 is the only derangement. Okay, but now if I have more things, like suppose I have n equals 3, there's a whole bunch of them. What are they? Can anyone give me, you can type into the chat if you want, it's just like, give me a bunch of derangements of 3 things. Remember, nothing can go into its own original place. Okay, I see a 3, 1, 2, I see a 2, 3, 1, 3, 1, 2. None of those is in its original place. I saw a 2, 3, 1. It's actually kind of hard to list these. Are there any others? So I can't put the 1 in the 1. So I have to start with a 3 or a 2. Yeah. Actually, are these the only two? That's it. Okay, good. By the way, you can see it's actually quite hard to think of these. It's easier to list things that are permutations, but derangements are tough. So these are the only two. Are the only two. Okay. So I have this, and the question is like, how many derangements are there for n things? Well, at first this question looks kind of, how might we do it? Well, you could try to say, let's see. I could start by saying, how many ways can I decide what goes first? N minus 1 ways, right? There's n minus 1 ways to decide what goes first. But then the whole thing breaks down. Do you see what I mean? Like, if I said I just throw something into the first position, as long as I don't put a 1, that's okay. So it's n minus 1. Times, now suddenly you need to say how many things can I put in the second position. But now it gets really complicated. So this is hard because even if there's n minus 1 choices for the first element, for the first entry, first thing, then somehow the next thing depends. The number of choices for the next thing depends on what you put in the first thing. Can someone explain why it depends? What might I have put into the first spot that would screw up this thing? Raise hand, Christopher.
Well, the number of choices you have for the second depends on whether you put the second object in the first spot or not.
Yep. Since the number of choices for the second thing depends on whether or not you put two for the first thing. Okay, cool. So that means it's not a simple multiplication. Then what could we do? What kind of technology do we have that could try to solve something like this? Aha. Is that Sarah? Sarah.
I was thinking that we could do like inclusion, exclusion.
How about we use the thing we've just been learning this whole week? That would be a great idea. And maybe that's why this question is here. Yes, we're going to use inclusion, exclusion. That's a fantastic idea. So if we're going to use inclusion, exclusion, we need to now think about what are these sets, right? We want to go and count the number of ways I can do a permutation where nothing is in the right place. So let's go and start thinking about what that looks like. Just a second. Something is very fishy with the computer I've got here. I'm going to quickly double check what's going on here. It might be that there's some random process taking up too much processing. Oh yeah, Zoom. Don't worry, you guys aren't going to disappear. This is a different Zoom. Go away, Zoom. Go away, Google Chrome. Maybe now it will actually run faster. Okay. Here we are. So we want to use inclusion, exclusion. And so in order to do that, inclusion, exclusion, that didn't help. I need to define a bunch of sets. So I'm trying to count how many ways that I can do these rearrangements so that nothing goes in the right place. What might be a good way to define some sets? So A1 is going to be the set of something. It's like the set of arrangements where, anyone have a good idea? Advait.
You could say that it's the set of arrangements where at least one element is fixed.
At least one element is fixed. So you're saying it's where, so you're saying set of arrangements where at least one of the things, okay, you use a technical word, element. Element is a thing. At least one element stays in the original place. Okay, I could do that for my A1. If I did that, then I guess I would be, as your idea that A2 is the one where at least 2 are in the same place? Is that what you're thinking?
And you can just count all the things that fix some element, and then like subtract it from the total to get the ones that fix no element.
Okay, so that's one direction we could go in. You're like the number where at least one element stays in place, at least 2 elements stays in place. I think maybe we want to be a bit more specific on what these mean. I see other people had hands. Eric, did you want to raise your hand? You're saying like have exactly one element fixed, right? So that's another way. Another way that we could think of this is like, here are different possibilities. We're trying to figure this out. Or it's like where exactly one, right? And then this one might be exactly 2. But maybe there are other ways. Like, what other ideas do we have? Andrew. No, Andres. Andrew. No, that is Andrew. That is Andrew. I just can't read the letters. Andrew.
I was going to say what the other guy just said. You just fix one element at a time.
Oh, can you expand a bit more about fix one element at a time? Because I'm not sure I understood that to be what this is.
Oh, well, it's just like for each set you take for inclusion and exclusion, it has exactly one of the elements takes in its position, and then you do all the rearrangements for all the others.
Okay. So that's actually the one I want to use. That may have been what everyone else is referring to, but that's going to be the easiest to count. There might be other ways to try to solve this, but I just wanted to write all of these out as like, they're all things you might think of trying. But the easiest one to deal with is like what we'll do in the white color on the right, or it's the one where like the 1 stays in place. The 1 stays in place. And the other one is, or the 2 stays in place. But now importantly here, when you say the 1 stays in place, more stuff could stay in place too. It just says that the 1 is staying in place and maybe more. So I'm just going to emphasize that here. The 1 stays in place and maybe more do. All right, so whenever we say the 1 stays in place, it means the 1 stays in place and maybe more stuff stays in place. And maybe this is actually what everyone meant when they were writing these previous things, but I just wanted to put all the ideas out. And we are going to be focusing on that last batch. Okay. Why? Well, I thought we wanted to find out how many derangements there are. Derangements is where nothing stays in place. Can someone tell me what this has to do with derangements? Suppose I define the A's this way. So A1 is 1 stays in place. AN is n stays in place. Braden.
Well, the union of all those sets is going to be all of the all of the arrangements which are not derangements.
Okay.
Just subtract them out from the next one.
Great. So that's A1, here's A2, and so on, and they just keep going. And of course, they do more overlapping. It's not like a big chain, right? They just like, there's all these different sets, and they're all like overlapping in some weird ways, looking like that. Here's my AN. And when you do all of that, what you care about is how much stuff is inside these blobs. No, you care about how much stuff is not inside these blobs. The derangements are outside. The derangements are out here. So what I find out is that the number of derangements is equal to what you just said is n factorial, which is the total, minus the size of the union. A1 union AN. Fantastic. So I just need to use inclusion exclusion now. We have a formula for the union, right? So let's go and figure out what the union is. Okay. Now the inclusion exclusion tells me that the size of the union, which I'm going to write like this, A1 union ... union AN is equal to the size of the A's, A1 plus all the way to AN. I'm trying to think if I want to do it that way. I'm going to use a new line actually. I'm not going to write it that way. You'll see soon why I'm doing this. I want to do a new line so that I can write some stuff near it. That's going to be the size of the A1 union, no, plus all the way to the size of the an, okay, minus the two things, a1 intersect a2, minus, plus the 3 intersections, and then minus the 4 intersections, all the way down to plus or minus the n intersection. Oh, the n intersection I can write. It is simply a1 intersect all the way to an. Okay, I left all of this so that I have a second column because I want to write the second column where there's space. Let's see what these are. What's the first one? What's the contribution of all of the size of a1 plus the size of a2 up to the size of an? I want just that one row. And for that, I need to know, like, how big is a1? How many ways can I do a rearrangement where 1 stays put and I do whatever I want with the rest of the stuff? Aaron. Good. What you said is there's n of them times n minus 1 factorial. And the reason for this is because I have n of those different sets, right? I have n of those different sets, and each of those sets has n minus 1 factorial ways to rearrange where I stuck that thing alone. Is that clear to everyone? That's nice. Okay, what about the next row? How about if I'm taking all of the pairwise interactions? Dhruva. Good. I'm going to write the n choose 2 in front. N choose 2 times n minus 2 factorial. Okay. That seems nice. Let's do the 3 intersections, and then hopefully we'll see some interesting pattern. What's the 3 intersections? Oh, by the way, why was it n choose 2 times n minus 2 factorial? It's because there's n choose 2 ways to decide which ones you're going to intersect. And now once I decided I want to have like a5 and a7, that means 5 is stuck, 7 is stuck, and the other n minus 2, do whatever you want. That's n minus 2 factorial. Yeah? So what is the deal with this 3 intersections? Sydney.
You would have n choose 3 times n minus 3 factorial.
Okay. At this point, we're hunting for a pattern. Well, I mean, we see a pattern. It's a pretty clear pattern. It's like n choose something times n minus the something factorial. But is there a way to make this pattern look more pretty? It turns out there is. So it's just like not fun to write algebraic expressions where you have an n choose 3. Is there an easier way to write this pink thing where I don't have to write an n choose 3? Christopher.
If I'm not wrong, those all come up to n factorial, right?
Oh, very interesting. So I wrote an n factorial there because, okay, what's n choose 3 anyway? Let's just go over here. N choose 3 times n minus 3 factorial, that's equal to n minus 1, n minus 2 over 3 factorial times n minus 3 factorial. Is that okay? So there is an n factorial that comes out. The numerator is n factorial, but there's an extra 3 factorial on the bottom. That's going to be important. So what do we see here, Eric? I think what you're saying is about the same. I think what you're saying is, look, same deal happens there. N choose 2 is n times n minus 1. And then the n minus 2 factorial multiplies you all the way down. So you get an n. Yeah?
On the left, just collapse the n.
Yep, so you collapse that into n factorial. And the denominator is 2 factorial. Okay, what's the pattern? How about the very last one? What should the last one be? Braden.
It would just be n factorial over n factorial. We don't, and then, yeah, it'll just be 1.
And that's 1. And do we believe that it's 1? Well, if you look at it, it's like, how many permutations are there that the 1 sticks there, the 2 sticks there, and the 3 sticks there, and the n sticks there? Like, what else is there to do? Nothing else to do, right? So it's perfect. It's 1. It's exactly as you'd expect. Okay, so now I have a formula. The number of derangements is n factorial minus all of this stuff. Do we want to rewrite the blue thing? The blue thing was n times n minus 1 factorial. What might be a good way to rewrite the blue thing? I want to make it look weird. Sean?
N factorial?
Yes, you could, but I said I want to make it look weird.
Factorial.
N factorial over 1 factorial. Why not? Over 1 factorial. Okay? So if I put everything together, now I have a formula for the number of derangements. It's going to be n factorial minus all this stuff. So the number of derangements is equal to n factorial minus n factorial over 1 factorial plus n factorial over 2 factorial. Remember, the thing is like flipping back and forth with the signs. Minus n factorial over 3 factorial plus dot dot dot, and eventually either plus or minus, I don't know which one it is. Well, I mean, I could figure it out based on the evenness or oddness of that. What a weird formula. There's something I'd like to do to clean up this formula a little bit. I want to clean it up by making it look more weird. As in, I have like a n factorial over 1 factorial, 2 factorial, and all that, and I've got this guy lonely here, an n factorial. Anyone want to help me make something into it that will make it look a little weird? Dhruva? 0 factorial. Why not? Let's put it over 0 factorial. That's still true. 0 factorial is 1. Now what's this? This is actually kind of interesting. You can factor out an n factorial. Everything has an n factorial. And there's some other stuff left over. All right? So I'm going to go into the next screen. I'm out of space on this one. But I wanted to get all the way down to here so you can see nice formula. Number of derangements is n factorial times. It's going to start out with being 1 over 0 factorial. And then minus 1 over 1 factorial plus 1 over 2 factorial and so on, going on all the way. Okay? So what we now know, looking at this, yep. So now I know the number of derangements is equal to n factorial times 1 over 0 factorial minus 1 over 1 factorial plus 1 over 2 factorial minus, and so on, all the way to either plus or minus 1 over n factorial. Okay. Now, what might this be? It's a big sum. It's kind of annoying. What's this? Shanai. Oh, something previous. Okay, that's fine. So I have this mysterious thing. It's like, by the way, oh yeah, you should be happy about the n factorial. Why? Because we're counting the number of permutations of some type, right? And the maximum number of them is n factorial. So the number of them that are derangements is n factorial times something. What's this? Andrew.
Is it like the Taylor series of something?
The Taylor series of something. I like where you're going. So what you just said is you've seen that somewhere before. That's the Taylor series of, can you give me a function which has Taylor series that looks something like that, and we'll try to plug it in?
Maybe sine?
Okay, let's figure this out, right? So what's the sine Taylor series? Sine x Taylor series. What was that? That was x, I think it's x over 1 factorial minus x cubed over 3 factorial plus, oh, that doesn't look like an exclamation point, over 3 factorial plus x to the 5th over 5 factorial, and so on. Okay. That's for sine. Are there other functions? Because the sine is like, it's close to that. It's like, I'd like to throw in maybe an x equals 1 or something. But what else could I use? Benjamin.
It would be like e to the minus 1.
Ooh, you want to use e to the x. E to the x is the easiest Taylor series. It's 1 over 0 factorial plus x over 1 factorial plus x squared over 2 factorial and plus so on all the way to x to the n over n factorial. No, it keeps going. Not just x to the n over n factorial. It keeps going. Plus so on. And so what you said is it looks awfully like what we've just done is we've put in e to the minus 1. E to the minus 1 now is just 1 over 0 factorial minus 1 over 1 factorial plus 1 over 2 factorial and so on. So that means that this is really, really close to 1 over e, right? It's like a Taylor approximation of 1 over e. So that's telling you that the number of derangements is something like n factorial over e, because that's e to the minus 1. But that's not satisfying. I mean, come on, we're doing math. How can we get an answer where we say the answer is about n factorial over e, right? First of all, n factorial over e, that's not an integer, right? So, for example, if you just decided, like, how could this possibly be a good formula? Imagine that you just threw in n equals, like, let's make up some big number. N equals 12. If you threw in n equals, no, I have a better one. Let's suppose we throw in n equals, like, oh, the factorial is going to be way too big. But let's put in, like, n equals, like, 20, all right? If somebody told you, look, the answer is 20 factorial over e, is that a whole number anyway? No, of course not, right? So let's just look at this. Like, I'll call it fun. Okay, this is just for fun. What if you put in 20? This is totally not an integer. Not an integer at all. Actually, anyone close to a Wolfram alpha? What is it? I mean, of course it's not an integer. What is 20 factorial over e? Can anyone tell me what this is? Type it into the chat, please. I guess if I had internet connection on this, I'll just type it in. Oh, it's a big number, that's true, but I want Wolfram alpha's thing. No, not all this scientific notation nonsense. Okay, you know what? Oh, I have a calculator. All right, we're going to go old school. Just a second. What's this? So if I went to this, does this work? 20 factorial? It does. Ah, good. Let's get lots of precision. 3 digits of precision. No, that doesn't work. Darn it, this doesn't work. All right, hopefully somebody else has a better job. Okay, so the problem is that on my thing, it'll give it in scientific notation, which is annoying. But now we got something coming from Chris Lacken, and if I could read it. Okay, so what I saw from Chris Lacken is like, there was some number, blah, 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 blah. And what was after the decimal point? 0.95. Is that right? Do I have that right? 0.95. That's kind of cute. Pretty close to a whole number. Hey, let's do something else for fun. This is why you really need Wolfram alpha. What if you did 100 factorial over e? Something. I want to know what's after the decimal point. This will be fun. What if you use Wolfram alpha, put in 100 factorial over e, get all the digits, and what's after the decimal point? Clearly, Wolfram alpha takes a while. Either that or copy paste takes a while. Either that or we need to pay for the paid version of it. I'm not sure which of these is the case. Uh-oh. What's this? 0.99015. Okay, you know where I'm going next. Let's just do some odd number. Suppose I went to 201 factorial over e. What's that? 201 now. And I just care about the stuff after the decimal point.
0.00492.
Oh, I have to make them so big. 0.00492, is that what you said?
Yep.
Why did I have to make them so big? It's so that I can show you something cool. What are you noticing that does not deserve to be true at all? There's something really weird here. It converges to an int. Yes, who in the world would have expected that n factorial over e converges to an integer? Does it deserve to? No, what's e? This weird number, right? Like e is the most ridiculous number in the world. Actually not. It's the base of the natural logarithm. You should not be surprised whenever weird stuff happens with e. Isn't that the thing in this e to the pi I plus 1 equals 0? It's a very interesting number. And so something weird is going on here, where somehow, if I take n factorial over e, it gets really close to a whole number. And that's actually related to the fact that this approximation is a really good approximation. Ooh, what's this? Look at the plot. Chris has made a plot. But what's actually true is that this approximation is not very lousy at all. In fact, the number of derangements, you can prove mathematically, is always this thing rounded to the nearest integer. Like, that's cool. Like, this thing rounded to the nearest integer. First of all, how many math formulas are do a bunch of stuff and round it to the nearest integer and that's the answer? That's very rare, especially when there's an e involved, okay? But now let's go ahead and prove that. So the really interesting thing here is that this thing here is actually really good. Okay, now if that's the case, I've got to prove it. How do I prove it? Well, I need to go and compare the difference, right? When I say something is really good, what I mean is if I subtract the two sides from each other, that gap should be really small. Does that make sense? So what are the two sides? On the one side, I have this n factorial times this part of the Taylor series, and it stops. And on the right side, I have the n factorial times like the infinite Taylor series. So what's the gap? Can anyone tell me what's the gap between them as like a algebraic formula? It'll have dot dot dots inside it. What's the difference between them? Yes, Sarah.
It's like the sum of 1 over n plus 1 factorial times 1 over plus 1 over n plus 2 factorial, blah, blah, blah.
Yeah. It's like from all of these like over factorials, where it's the bigger factorials, okay? So what I want to emphasize is the gap between these two is going to have an n factorial, and then it's going to have all of the 1 over more factorials. Like more meaning n plus 1 and onward. I will write that on the next screen. The gap in the approximation is exactly it's going to be n factorial times 1 over n plus 1 factorial, and then minus 1 over n plus 2 factorial plus 1 over n plus 3 factorial minus dot 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 forever. Okay, now if I want to know how big something is, I want to bound now. I want an upper bound. So I'm going to write an absolute value around it. Is that okay? Because that's what I'm doing. I want to know what's the size of this gap. So it's absolute value of this. If that's the case, there's something nice you can do about absolute values. If I want to know the absolute value of an arithmetic expression, that's always less than or equal to the sum of the absolute values of each of those individual terms. This is always less than or equal to absolute value of each of the terms. N factorial over n plus 1 factorial, absolute value, plus absolute value minus n factorial over n plus 2 factorial, plus dot dot dot. Well, let's just write the third one just for good measure. Plus n factorial over n plus 3 factorial plus dot dot dot. Is this understandable to people? If I was doing a bunch of arithmetic and then do absolute value, well, that's less than or equal to if you just like absolute valued each of them in advance. Because if you do the arithmetic first, you could potentially cancel some pluses and minuses against each other. This actually has a name. Does anyone know what I've just used? It's a name that you'll see in math all the time. I've used an inequality. Aha, I already saw someone type it. It's called the triangle inequality because of triangles. I always think of it as triangle inequality says shortest path between 2 points is a straight line. And so when you're adding things and subtracting things, it's like something like that. Yeah, it's like somehow if I was gonna like move along the number line, like if I'm moving by a minus amount, it's like how much did you travel? Well, even though I went in the minus direction, I traveled like 1 unit or something. So it's like if you want to know how far you've traveled, just like an upper bound is how much did you step each time in any direction. Add them all up. Okay. Take analysis and you'll never forget it. Yes, that's correct. If you go and take an analysis class, the whole game is called Triangle Inequality, Triangle Inequality. It's good stuff. And actually, I use triangle inequality in graph theory too. It's one of the most useful principles in mathematics. Now, why did I write this? I wrote this because now I can forget about the minus signs. I just don't like the minus signs. They're annoying. But I can also simplify this. So this I can simplify as, I'm writing an equal sign. This is 1 over n plus 1 plus, I'm going to write the next one as 1 over n plus 1, n plus 2. The next one is 1 over n plus 1, n plus 2, n plus 3. Okay. Now I want an inequality. I'm trying to show that this error is not so big. So I'm going to continue on, and I'll write another inequality. Honestly, I could have written less than instead of less than or equal to, but I only need less than or equal to, so it's fine. Is there a way to write down some other things that are easier? I would like to know a formula for the sum of all this stuff. And it's no fun to sum up this, like 1 over n plus 1, and then 1 over n plus 1, n plus 2. That's kind of inconvenient to sum. But there's something else I can use, advit.
You like partial fractions it or something?
You could, except I'm not smart enough to do that.
And this suck. Okay, can you instead factor it?
Factor it is also a bit hard because I've got infinitely many things. I want to throw away stuff. I want to say this is just annoying. 1 over n plus 1 and over n, like n plus 2. Is there something simpler? Chris?
You could integrate it, so it's going to be like ln of n plus the n minus ln n plus 1.
Oh, okay. So we could try to use natural log to integrate. That's another direction we can go in. But I think you guys are used to solving questions precisely. I'm being sloppy and lazy. And most of the time people don't do that. So June, did I read your name right?
Just do n plus 1 squared.
Yeah, let's do n plus 1 squared because we're lazy. Okay, and it'll be good enough. So, by the way, this is totally true because it's like, look, I wrote a less than or equal to, right? And if I have a denominator and I replace it with a smaller denominator, the answer is bigger. If I have a pi and I divide the pi by only 3 people instead of 10 people, everyone gets more pi. So that's why I can do this. And the second one just becomes, the third one just becomes 1 over n plus 1 cubed. Now, why did I do that? I did that because we know how to add that. What's a good formula for adding all this stuff together? Ooh, Cindy. Geometric series formula. So the geometric series formula is the first term, 1 over n plus 1, over 1 minus the common ratio, 1 minus 1 over n plus 1. We can simplify this. That's not so bad. Multiply the top and the bottom by n plus 1. I think I did that right. Yeah, multiply the top and the bottom by n plus 1. So that's going to be 1 over n plus 1 minus 1. Oh, 1 over n. Why is this good? What have we just found out that's like really remarkable? I want to give more people a chance that maybe haven't said anything yet. This is a fun punchline. What's so good here? Shania. Okay, so the important thing is, what was this gap anyway? This gap here was somehow the gap between n over e factorial and the number of derangements. No. What? N over e factorial? You don't do that. No. N factorial over e. There's no such thing of the... Well, not that there's no such thing. You could do the other thing, but it's ridiculous. And the number of derangements. Okay? And that's the gap, right? And the gap size, you're saying 1 over n. For example, if n was at least 2, then you're telling me that the gap is less than half. Actually, now it's telling me I don't want to use these less than or equals anymore. Because if I found out that the gap is less than or equal to half, I don't know which way to round it. You know, like in some sense, if the gap was exactly half, then it's a half integer. But it won't be, because e isn't even rational, right? So what I can do here is I'm going to erase out the less than or equals to. I'll remove the equals to, because it's actually less than. These are true. The reason both of those got erased is because, well, I had both pluses and minuses. So the triangle inequality actually tells me more. It's like if I combine both pluses and minuses, well, then if I just pretended all the minuses are pluses, then it's not right. It's not equal. Okay? The second one is also not equal because I changed an n plus 2 into an n plus 1. Okay? So now what I've just found out is if I look at the number line, wherever they are, I mean, sometimes it's bigger, sometimes it's smaller. But whatever it is, we've got these two numbers, n factorial over e, number of derangements. And what's actually going on is the number of derangements, let's give that the green, the number of derangements is actually an integer. It better be. Number of derangements has to be an integer because it's a number. We counted it. It's a real number. Oh, that's not what I meant. It's an integer. Real number is like it's also a real number, but it happens to have no fractional part. So it's a legitimate integer. And so what I've just found out is that this gap here, the upper bound on the gap size is strictly less than 1 over n. And what was just mentioned by Shanai is that if n is 2 or more, then that means that that weird n factorial over e, it's within half of an integer and within half of the integer which is the answer. That means that if you round it to the nearest integer, you actually get the legitimate answer. That's exciting. So let me write down the conclusion. So for any n which is at least 2, if you round n factorial over e, this is exactly equal to the number of derangements. That's super cool. Okay, but how about n equals 1? You never have, don't worry about derangements of 0 things. That's silly. There's nothing going on. We won't even worry about what that means. How many derangements of 1 thing are there? Can I hopefully make this formula true also for n equals 1, Advait?
Sure, you can. There are no derangements, and 1 factorial over e is like 0.3 or something. So like you're good.
Yes. So the key is like even though we've just proved this for n at least 2 by using all of this fancy work, if n equals 1, I can prove it by the I just did it. I didn't have to do any work. It's a small thing. When n equals 1, let me just write that down, maybe underneath. And if n equals 1, the number of well, let's write this way. Round of 1 factorial over e. E is this like 2.718 thing, right? So if you round it, you get 0. Because it's like 1 over 2 point something. And that's actually equal to the number of derangements of 1 thing. There aren't any. And that's it. So we've actually just proved a beautiful formula for the number of derangements of n things. It's just take n factorial over e, round it to the nearest whole number, and that's it. There are very few math formulas that are this surprisingly nice. Somebody had asked me, why did you ask to calculate such big factorials over e? Now do you see why? And do you see something really interesting about the numbers that we got? Let me go back. Do you see anything about this that is somehow satisfying in light of what we've just figured out? Braden.
The distance between the closest integer is very close to 1 over whatever we're taking our factorial of.
Yes. What is 1 over 20? 0.05. Oh. What is 1 over 100? 0.01. How about 1 over 200? 0.005. This is like awesome. And now you might say, wait, that means that triangle inequality wasn't so far off. How could it be? You know, I thought we threw away some stuff. Like, how can it be? How do we rationalize the fact that, somehow over here it looks like our approximations are almost on the nose, but I thought we were wasteful. I thought we threw away some stuff. Well, there's a reason why. Christopher.
I mean, as n gets bigger and bigger, the stuff that you're throwing away gets infinitely small.
Yes.
The approximations are getting closer.
Yes, actually the approximation is pretty darn good, because if you think about it, what we actually swapped from minus to plus is what's called the second order term. The second order term is the one which has over n plus 1, n plus 2 anyway. Imagine if n is 100, then this is like 1 over 100 for the first guy. But the second guy is already 1 over 10,000. It's really, really small. It's like 4 decimal places back, so it doesn't make much difference. So this particular approximation costs you almost nothing. And the second approximation over here, it also costs you almost nothing because it's again in what's called the second order term. The main term is the first one, 1 over the n. So that's actually why this whole thing works out. And it's really surprising, it's really neat. And I guess that finishes the derangements, that finishes the inclusion, exclusion, and that finishes our week. Next week, we're going to go on to a different topic, and then we'll go and do the exam on Friday. So thanks, everyone.
Thank you.
Thank you.
Yep.